Coordinate transformations in linear algebra. I've always found them tricky, and I'm not the only one. It's not like the idea is hard, it's just getting the details straight. So I've spent a while coming up with a scheme to try to clarify it a bit. Here's what I've come up with. Suppose we have the standard basis vectors e1 is 1, 0, e2 is 0, 1. We have another basis, a1 is 2, 0, and a2 is 1, 1. And I've got a vector, v, 3, 1, that I want to describe in the a basis when it's already described in the standard or e basis. So what do we do? The first thing is to recognize that we don't want to write it just like this. Instead of a little subscript e, let's be explicit about it. The vector v is actually e1, e2 times 3, 1. You have the basis vectors for e and the components for e. When you multiply that out, you get 3e1 plus 1e2, and sure enough, that's the correct thing. Okay, seems like overkill, but when we change bases, this is going to be helpful. Now, e1 is just 1, 0, e2 is 0, 1. So the reason we've been ignoring it most of the time is because it's the identity matrix. So that's vector v, the identity matrix times 3, 1 in the standard basis. It turns out that if we want to write v as being constant 1, a1 plus constant 2, a2, that will also rewrite as a1 column vector, a2 column vector, times c1, c2, the components in the a basis. And that will be vector v. Which means if we can get this a matrix, they call it the a basis matrix, in front, then what's left has to be the components. Now this makes it fairly straightforward what to do. If we are starting out with v equals 1, 0, 0, 1, 3, 1, and what we want is to start off with the matrix A. The way to fix that is to have that identity multiply the A matrix. 2, 0 in the first column, 1, 1 in the second. But then to not mess up the value, because we want to talk about the same vector, we're not transforming the vector, we're just redescribing it. We also need the inverse of that matrix. Since these multiply to the identity, we still end up with 3, 1 in the standard basis. But if we take this as being the basis and this as being the vector, what we find is that 2, 1, 0, 1 times 1, 1 is vector v, which means that this vector 3, 1 in the standard basis is the vector 1, 1 in the a basis. So it wasn't actually a bad calculation. All you have to do is make sure that you end up with the basis matrix in front. And then whatever you had to do to the vector to make that work is what transforms it into the vector you're looking for. Now let's do a slightly more complicated example. We have the matrix A and the components 1, 1 to make the vector v. I'd like to know, if I know the basis vectors B to make the basis matrix, what are d1 and d2? Well, we're starting with A, 1, 1. We want to end up with B and then something else by multiplying stuff in the middle. So we want to multiply by A inverse to get rid of that A, and we want to multiply by B, so that we'll end up with B there. Now, to undo that, we then have to multiply by B inverse and by A, followed by 1, 1. If we do that, this becomes B, the basis matrix, and this becomes d1, d2. So I think this makes it a lot more obvious what to do to perform the transformation. Any vector you want to think of as being not just the two numbers, but the basis matrix times those two numbers. Most of the time that's the identity, but it helps to remember that it's there. And we modify it by putting matrices and their inverses in between the basis and the components. Okay, now for the more complicated situation. We have a transformation T going from a space V to a space W, and V is 3-dimensional, W is 2-dimensional. Suppose the transformation is given to us using the standard bases for both. So we have basis E3 for V, basis E2 for W. And the transformation is written in terms of taking an E3 vector and producing an E2 vector. So for example, 210103 could take an input vector of 112 and produce the output vector 37. All of that in the standard basis. Now what we'd like is to have another basis for V, A, and another basis for W, B. So we'll have a B1, B2, and we'll have an A1, A2, A3. And I would like to take this transformation and rewrite it so that it will take an A vector and turn it into a B vector. So how does this work? The first thing we do is we use our trick. Any vector should be written with its basis. So we're starting out with E1, E2, E3, 1, 1, 2. E1, E2, 3, 7. That's our input vector, that's our output vector, and there's our transformation. We now want to rewrite this so that we get this into the basis A, and we want to rewrite this so we get this into the basis B. So we do the usual thing for each of them. So we have our transformation T in the E basis, I'll just abbreviate it. And then we have E3. And we would like this to be an A, so we put an A there, and then an A inverse, and then our vector V, 1, 1, 2. We haven't broken anything because we just multiplied by A inverse. Meanwhile, over here, we've got E2, and we would like to be basis B, and then we multiply by B inverse, and 3, 7. This is the basis, and this is the vector, written in terms of B. This is the basis, this is the vector, in terms of A. So if what we actually want is just to take the input vector and produce the output vector in basis A to basis B, we could undo this matrix multiplication here. We could multiply by the inverse of E2B. In other words, B inverse here. So B inverse, T in the E basis. E3 is just the identity. So then we have A. And that produces vector V expressed in A. And that leaves here the vector W expressed in B. So B inverse TA is the transformation. I find that a lot easier to keep track of. Hopefully you'll find that helpful.